Start time should be now. Guess we got something a little wrong in the scheduling here, but yeah, we'll be starting Monday through Thursday at 10:30 every time. Today, we're going to talk about complexity analysis. Our overview on complexity analysis is the part where we start to look at, in a theoretical sense, how programs run in terms of time and space complexity. That's what we're going to start with. And we ask this question: given an algorithm, an input size n, how many steps are needed? How much execution is needed? And steps are a thing that we'll look at calculating. In the end, we're going to find a way to not use the steps for counting, but it still is going to be representative of if we had counted the steps. We imagine each one of these steps taking a constant amount of time. This is like a clock cycle, or maybe even as low level as an instruction, even though some instructions may take more than one clock cycle. We don't worry about the distinction there, because we're looking to see, as our input size grows, as this n increases, how does that affect the number of steps changing? We look at that trend to see if we take n and we double n, do we do twice as much work? We say that that's a linear function there. If we double it and there's 4 times as much work, we're looking at something that's quadratic, and so on. How do we measure the complexity? Well, for the purpose of these slides, we're going to be talking about the rate of growth as this function f of n. And then we'll use big O notation to give us a way to measure the complexity of that function, the big O of f of n. And we'll talk about big omega, we'll talk about big theta, and how they all play into this. So this is important, of course, because before we write code, a lot of times it'd be great to know what's going to be good code. No one wants to spend a lot of time writing and debugging only to find out that now that this is perfect, it's still nowhere near good enough. So we look at this and see how the algorithm is going to perform on various inputs. If we've got a lot of n, or if we've got a guaranteed small n, or completely unbounded, we need to know these things so that we can make some choices on how they're going to perform before we write them. So we'll look at some metrics here. Here is an array. We'll call this an array of n items. You see there's a red square in the first slot, there's a blue oval in the last slot, and right there in the middle is a green triangle. If we're going to use a linear search, that's kind of the basic thing that we can do, is like just look at all of the things. If we process all of the things, we're going to be doing something linear here. So if we use a linear search over n items, trying to see how many comparisons it's going to take to find some particular item. If I look in one place and find it, that's my best case. That's my single comparison, I've found it. My worst case is when the thing that I'm looking for is possibly that blue oval at the end. I start at the beginning here, look at all of the items until I get to the end and find it. Or if I'm looking for the purple star, which doesn't exist, but I still have to look at all of the items there to find out that what I'm looking for isn't there. So this is n comparisons. On average, we're going to get somewhere around the middle. The green triangle there is in the middle, and that's about the amount of work we're going to do on average. Sometimes it's a few spots before the green triangle, sometimes it's a few spots after, sometimes it's a lot of spots before, sometimes it's a lot of spots after. But our average case is this n over 2 comparisons. So you can think of the best case as having the least number of comparisons, or the least amount of work to be done. You're given some ideal input. If we perform this analysis over the inputs of a given size, you can see that my best case happens when what I'm looking for is in the first place I look. The worst case requires the most number of comparisons. This is when I've been given hard input. the data happens to be found in the last place I could possibly look, or even worse than that, what I'm looking for doesn't exist, and the only way I can find it is by looking at everything to know that it's not there. The average case, we talked about that. This is our sort of random input. If my input is randomly generated, it will usually give me average case results. So it says they're given any input. That's probably any input. We could really find some bad cases in there, or we could really find some easy cases in there. But if you look at all of the average inputs that get generated, some of them are really good, some of them are really bad, and a lot of them are right there in the middle, and they all balance out to be that N/2 average. So what affects runtime? Of course, we've got the algorithm. Up front, that's the thing that we're always wanting to choose the best of. We've got an n-squared algorithm and an n-cubed algorithm. We're probably going to take the n-squared algorithm all the time. The only time I might take something that's a worst time complexity is that worst time complexity might offer some better memory complexity. And if I've got a really a really constrained system where I have some memory deficit there, then I might choose an algorithm that's a bit slower, because memory and time are kind of two sides of the same coin. If you think about the way computation works, if I've got some value, I don't have to calculate it. But if I don't have the value stored, then I have to calculate it. So I've either got to do some work or use some space. So oftentimes we'll be looking at that as a trade-off on how do I decide when to use an algorithm, or how do I decide when to use a particular container or anything like that. Implementation details, of course, will affect runtime. We'll see that as we learn how to be better programmers in 281. We will be getting some regular considerations. Don't pass objects by value. That just makes a copy, and then we destroy the copy, and it is often a waste of time. Other things like, how do we index containers efficiently? How do we use algorithms that work on ranges efficiently? CPU speed, memory speed, or hardware things, of course, affect runtime. One of those things, though, is easy enough to fix by just spending a little bit more money and buying a better machine. We can't always do that, but if there's something that's mission critical for a particular company and they've got a server from 2005, they might just upgrade the server and make a huge difference there. So that could affect runtime. How things get built, we'll be trying to make sure that you use some good compiler options. We've got the O3 turned on for release builds in the 281 makefile, and the G3 can be turned on for debug builds. So the G3 is the highest level of debugging information that gets included with the runtime, so that then later on debugging tools can take a look at where they are in the code, and you can even see the code as you're stepping through it. That's because this executable was generated with debugging information embedded in it. The optimizations that come in the O3 build are pretty substantial. They do a lot of things that will give us more speed that we might not do ourselves. And so it's important to use those when you're trying to get graded on the autograder. Other programs, of course, running in parallel, they could be using the hardware. That'll affect the runtime. But one of the things that we're really going to be focused on here in the complexity analysis section is this amount of data processed. The input size is important. That N, the N that I'm processing, is really what's going to be important here. As we look at input size versus runtime, we're really looking at this rate of growth as being independent of all those other things. We're talking about hardware stuff, we're talking about programmer stuff. What we want to know is, how does my input size change my runtime? Does doubling the input mean doubling the runtime? So that looks linear. If I get 4 times as much information, does it take me 4 times as long? That's a great thing to compare there. As we look at this graph here, there's a blue line that's a straight line. That's representing something linear. And as input size grows, runtime increases proportionally. There's a red line on the graph here that looks to be a bit quadratic. So it's kind of a belly here, and then it swings up a little bit more sharply than the linear, the blue line above it. And that's something that we'll be looking at and being used to recognizing somewhat graphically, but definitely in code. We want to know, are these fast algorithms still going to be fast when the data is large, or is it just fast because we've got a small amount of data and it's just getting things done decently? So we've got to know what this input size n on the bottom is. How do we measure that n? We've got a lot of ways to do it. We could measure the number of bits if we really want to be down there and dirty in the hardware. Is there an int or a double that it's being processed? You think of an int as a 4-byte integer, a double as an 8-byte floating point value. Those take up 32 bits and 64 bits respectively. So that's one way to do it. If you count all of the bits involved, that will definitely be a reasonable way to count it. But it's also a lot of work. Sometimes we can just look at the number of items. Well, it's 40 ints or 400 doubles. And then we could be looking at the n really is at 40 versus 400, because if we double the n at 40, we're obviously doubling the bits there as well. So getting down to the bit level is really more than we need to, but that's the basics of what's going on there. We can be looking at the number of items, but then we have to know what counts as an item. When we're looking at an array of integer, is it the array? Is it one integer? Or are we processing things on a digit by digit level there? How deep do we have to get in there? When we're looking at a string, are we looking at several strings? Do we have to process each character in every one of the strings? So it's important to know what n is, because that's where we're going to be doing our focus. That's where we place our focus with this complexity analysis. So n is our input size, and we say that that's the thing that drives everything. Then f of n is the maximum number of steps that our algorithm is going to take while processing that data of size n. And then lastly, this big O of f of n is the complexity class. Here's the common orders of them. We start out with our quickest at the top here, constant time, big O of 1. Then we've got logarithmic time, big O log n. There's linear time, big O of n. Between linear and quadratic is n squared, we've got n times log of n. We'll call that log linear, or sometimes called linear arithmetic. Big O of n log n, that's where our really fast searches end up. Then other things we'll call polynomial. To be sure, linear is polynomial. Quadratic is also polynomial, but they're so small and so common that we just use those names specifically about that. And sometimes you'll use cubic in there if you're talking about a third order polynomial, but most of the time, once we get up above quadratic, we'll just call those polynomial time. This is where we've got n raised to some constant power. Faster than polynomial is faster than exponential. That's c to the n, where we've got some constant as a base raised to the n exponent. Now we're talking about some really, really slow algorithms as n grows. Even slower than exponential, we've got factorial, big O of n factorial, and then there's other things that go beyond that, doubly exponential and other things like that. But this is a common listing. We're going to be working a lot in these first 5. So we'll get used to seeing those sort of things, and we'll get used to feeling that behavior. Occasionally, you'll have to drop in something that's n cubed, but we really would like to avoid any of the others. We will have to work in the factorial space here in Project 4, but commonly we're going to stay up high in that quadratic and above when we're lucky. Here's just a graph of these runtimes all placed together. We see constant time here, the straight line across, that's blue. Then a really slowly increasing red line follows that as logarithmic time. Linear, and we see all of them. The one thing that's kind of interesting to note here, the two slowest ones, n squared and exponential, 2 to the n, see it looks like they're about the same. But that's just because we've got a really small n here. Down at the bottom of the graph, this just goes from 0 to n. And so n squared and 2 to the n kind of cross each other a little bit. Looks like they might hang out together forever. But when n gets large, there is no comparison between n squared and 2 to the n. And that's one of the things that's really important when we're doing our analysis. we always want to think of n as being something out of our control. If you're trying to control n, then you really are not analyzing the problem properly. And not only is it completely out of our control, but you can think of it as being really large as well. If you do that, then you're going to be safe with your analysis. So here's an input size example. I've got a graph up here with these 5 green nodes and 6 edges that connect them. And so the question is, what is n? Should I be measuring these vertices or nodes? Should I be measuring the edges? Do I measure the vertices and the edges put together? So we'll use V and E to determine which one contributes more to the total number of steps, where V is the set of vertices and the magnitude of V being the number of vertices, and E is the set of edges and the magnitude of E being the set of edges, or sorry, the number of edges that we have. So it's going to depend when we get into graphs on what type of algorithm that we're doing. We won't talk strongly about graphs until the second half. But some examples of graph algorithms will show us something like an E log V, or maybe an E times V, or a V squared log E. So in this case, sometimes it's based in one. I could have a V squared algorithm, right? So some of my algorithms are going to depend on one or the other, or even a combination of the two. So it's important to know, as you're doing analysis, what really is n. As we go from analysis to application, we know that if we keep these algorithm comparisons independent of hardware and compiler tweaks and all of that other stuff, we can still use this analysis to predict which one of these algorithms is going to be faster. If I've got large inputs, then I can see that my n squared time algorithms definitely take longer than my linear or big O of n algorithms. We generally ignore the constants that are involved there because they don't affect our asymptotic comparisons. N squared is the same as 5n squared, is the same as 100n squared in terms of analysis. As we're talking about asymptotically, these things behave like that. Obviously, a 5n squared algorithm is going to run faster than a 100 squared. A 5n squared algorithm is going to run faster than a 100n squared algorithm. But if you look at the way that those numbers shake out, when n gets really large, if we're talking about n being 100,000, and then we want to square 100,000, 5 times 100,000 times 100,000 is almost identical to 100 times 100,000 times 100,000. It's the 100,000 that makes a difference. It's the n that matters there, which is why we can also ignore other constants. If we say this particular algorithm is 5n squared plus 3n plus 50, when n squared gets really large, that 5 times 100,000 times 100,000 really blows away any additional small 100,000s or other constant values. That's our overview on complexity analysis. We'll be shifting on into counting steps here. This is our tool for understanding what n as our data size turns into. We talk about our big O. So we're going to count some steps, and for starters, we need to know, what are we calling a step? And this is a really basic way to do this. So what we're going to do is do a lot of hand waving and say, don't worry about a whole lot of sharp details. Let's just get a broad understanding of what's going on. So we're going to take these primitive operations, variable assignment, arithmetic operation, any arithmetic operation, comparison, array indexing, or a pointer reference, calling a function, or returning something from a function. We're not going to count data that's involved there in any of those things. But these things all take different amounts of time. That's why I say we're doing a little bit of hand waving. Not all arithmetic operations are the same. Arithmetic operations versus comparisons are not necessarily the same. Doing an assignment is not the same speed as something you might do with a comparison. Don't worry about it. We're just going to use these simple ways to do this and imagine that every one of these steps is a constant amount of time, no matter how much input is there, no matter which step it is. It's just a way to simplify this. So, counting steps in a for loop. The basic form of our for loop is this initialization, test, and update. So initialization happens once, the test happens every time that the loop completes, and then the update happens every time that the loop completes. But we're still not done. We've got to make that test one last time, and that's when it fails. And that's what gets us out of the loop. So we'll say that the initialization gets performed once, the test gets performed n+1 times, and then the update gets performed n times. So you imagine writing a for loop that never executes. So for I equals 10 while I is less than 10 plus I. That for loop would never execute because I starts out as 10 and we're comparing to see if I is less than 10, which it's not. So the body never gets executed once, but the test does get executed once. So that's how, when we look at these for loops on the next slide here, we'll see that that contribution from a for loop shows up as 1 plus 1 plus 2n steps, right? The one step is initialization. I've got n+1 as my test, and then I've got an additional n as my update step. So in this code here, we can think of any one of my steps taking any one of my operations taking one step. So in line 2, there's sum equal to 0. That's a variable assignment. We'll call that one step. In line 3, we've got a for loop there, so that's always just going to be 1 plus 1 plus 2n steps. And that's the overhead of the loop. It's not about what's happening inside the loop. We have to calculate that separately. But the overhead of just running a loop is 1 plus 1 plus 2n. Line 4, we see that's inside of the for loop, sum plus equals I. And that's indented over there on the step count, just like it's indented in the code, because we're going to multiply that by the size of that loop. So it only takes one step, but we're going to say that it contributes n steps to the overall comparison, or the overall calculation, because it's inside the loop. Those of you who are quick might say, wait a minute, that sum plus equals I, is that an assignment? Or is it arithmetic operation? It turns out it's both. And we could call that 2 steps if we wanted to. What would happen if we called that 2 steps? We change line 4 to 2 steps, and then we look at our total answer there. Our total answer is 4 plus 3n steps. So I've got the one step at the top, 1 plus 1 plus 2n steps in line 3, and then the one step in line 6. I'm getting an additional n there by multiplying line 4 by n. And since it's one step, that gives me the additional n. That's where the 3n comes from. If I were to say that that sum plus equals I is equal to 2 steps, then it's going to contribute an additional n. I'll say that my total steps is 4 plus 4n. Well, as I'm looking at this slide, it says counting steps polynomial. These are polynomial values here. If I look at the polynomial that is how many steps this takes, 4 plus 3n is a linear polynomial. 4 plus 4n is still a linear polynomial. And as we get into figuring out what the order of complexity of these things are, that's what we care about. So that's why we kind of do a bit of hand waving even on this early stage. 1 step, 2 steps, 3 steps. It turns out it doesn't matter how many steps go on inside your for loop, as long as it's the constant number of steps. As long as the number of steps inside the for loop doesn't change with how big the for loop is, how large n is, then we can say that this is a constant amount of work inside the for loop, and the fact that it happens n times is really what's important there. So we don't care about the number of steps in there. It could be sum plus equals I. It could take 100 steps for all we care. That's still going to make this a linear complexity analysis. How about this next one? Here we see that we've got sum equals 0 again in line 9. That's a one-step deal. There's a for loop in line 10, and these are beautiful for loops. I love a for loop that says I equals 0, I less than n plus I. That's how you should write for loops. Anytime you write something else as a for loop, you got to be really careful when you start trying to write for loops that go backwards with decrement. You need to do it from time to time. I won't disagree, but you just have to be careful. It's really easy to read and see a for loop that starts out at 0, goes up to n, and then just uses increments. For loops are count-controlled loops. That's why we write them, and that's the easiest, most straightforward way to write one. Sometimes you need to skip the first item. You might say, well, I equals 1. Then you have to be careful. How many times is this loop actually processing? So in line 10, I've got a very basic for loop. In line 11, inside of that for loop, I've got another very basic for loop, and I like that. Both of those, I look at them as having n as their upper count, and it's going to give me this 1 plus 1 plus 2n steps for the for loop itself. So the for loop in 11 that's inside of the for loop at 10 is going to give me 1 plus 1 plus 2n steps, but it's also inside of that outer for loop, so it's going to give me that 1 plus 1 plus 2n steps n times. So we can think of that inner for loop, just the overhead of that inner for loop itself is going to be 2n plus 2n squared steps that are going to be added to my overall complexity analysis. And then lastly, that plus plus sum inside the inner for loop, of course, that's going to be run as many times as n happens, or sorry, as the for loop in 11 happens. That's that j for loop. So n is going to go, a sum is going to go n times. This plus plus sum in line 12 is going to go n times, and each one of those n times is going to happen n times again. So that one step that's doubly indented there in line 12 in the analysis is really going to happen n squared times. All right, then we've got another basic for loop with a constant amount of work going on in it in lines 14 and 15. So there's a 1 plus 1 plus 2n, and that one step indented is going to be another n amount of work. And then we return with one step at the end. Add all of those things up, I get a complexity that looks like 3n squared plus 7n plus 6. What about those two increment-decrement steps? Line 12, line 15, plus plus sum. That's really the same as saying sum is equal to sum plus 1. So that's not one step, that's two steps. That's an arithmetic operation and an assignment. And I don't care, right? That's a constant amount of work. The inside of that body happens a constant amount of times. So you see here that in line 12, that happens, that's a constant amount of work, whereas line 11 is not a constant amount of work. When n is larger, line 11 happens more. It contributes more to this. Whereas every time I run line 12, it always takes the same amount of steps. It's that one step. Line 11, however, is going to execute more times. It's going to contribute more work when n is larger. So that's what we have to be aware of when we're starting to use step counting analysis. Most of the time, we're worried about things that happen inside of the loop. This constant amount of work in line 17, return sum, doesn't add much at all. It's part of that 3n squared plus 7n plus 6, but it's part of the 6. It's part of the stuff that doesn't matter when n squared really goes large because n is large. So this is how we can do this counting steps. What we're looking for is like, look at these two loops. I like to see the loops. That's where all of the work happens. Everything else is a constant amount of time. So we start out by counting steps, and then as we get used to this, we progress to just counting loops and see what happens there. So 3 and 4 give me a linear loop. 10 and 11 give me two linear loops, but one's inside the other. So that's n squared. Then I see what's going on in 14. That's just linear. So if I'm doing an analysis on function 2 and I realize that there's this n squared bit in 10 and 11, I don't even have to worry about what's going on in line 14 because that's just contributing a linear amount of work. So here I would say then this is an n squared algorithm at the bottom and this is a linear algorithm up at the top. How about logarithmic stuff? We talked about that as our second fastest complexity class, right? We have fastest being constant time, second fastest being logarithmic. How do we count logarithmic, or how do we recognize logarithmic? So this loop that we see here in line 3, this is not my favorite kind of for loop. It is not a very nice 0 less than n plus plus kind of deal. We start out, we've got 4i equals n. As long as I is greater than 1, I gets divided by 2 and set to this new smaller value. So as we start writing this out, we see that the number of times that this loop happens in line 3 is really all that's important. What's going on in 2 is a constant amount of work. What's going on in 6 is a constant amount of work. What's going on in 4 is a constant amount of work as well, but it happens however many times that loop happens. And so we need to figure that out. Down below here, we're going to say that that loop is going to run some amount of times. There's going to be some k times. We're trying to figure out what that k is. So if we start out with n, and then We divide n by 2, then we've got n over 2 items, and we divide n by 2 again, we've got n over 4 items. We keep dividing n by 2, by 2, by 2, by 2. Eventually we get down to this just one item here. While this is my division that's gotten me out there, I'm still stuck with the question, well, how many times did I actually do that? Well, if I start at the bottom and start doubling things, I said one item gets doubled to 2, gets doubled to 4, gets doubled to 8. Eventually I'm going to get to something that looks like n. And so the number of times that I double it is the same as the number of times that I get here. And so I end up with 2 to the k being equal to n, or the number of times this loop actually runs. So if 2 to the k is equal to n, to find out what k is, the number of times this loop happens, then I just need to take a log of both sides. I end up finding out that k, the number of times that this loop happens here, is something that looks like log base 2 of n. This is how we recognize things. When I see plus plus minus minus as my update step, if I've got a for loop that's got a plus plus or a minus minus, or plus equals something constant, plus equals 2, plus equals 4, those things are going to be linear loops for the most part. When I look at something that's got my range being cut in half, or I'm taking my increment step and doubling it every time I do my update. So here we see this I is being divided by 2. So there I'm cutting something in half. So if every time I cut my data in half, that is logarithmic behavior. So that's how we start to recognize this. When you're looking at for loops, when you're trying to evaluate them for their complexity, if you see a plus plus or a minus minus, chances are that's linear. If you see something that's got a division or a multiplication in there, now you're probably going to fall into something logarithmic. It might take a little bit more close evaluation, but that's my general go-to. If I see those things happening there, if I got some multiplication in my update or division in my update, I'm thinking that's probably logarithmic. And you can look at what's being divided by. Here we're dividing by 2 in line 3, so that means it's log base 2. But if I was dividing by 3, I would say it was log base 3. But divide by 4, I would say it was log base 4. In the end, however, I'm still going to look at all of those things as being logarithmic. They kind of work together. Here's some examples of log n time. This log b function, lines 1 through 9. How do we recognize what's going on here? We've left our for loops behind. For loops aren't the only thing that matter, though. It's loops in general. So there's a couple of while loops in these two functions. And this log b function has a while loop, and that b search function over there has a while loop as well. So now we still need to do the same thing. How many times are we going to run this loop? It's easy to see in a count control loop. We call those for loops or count control loops. While loops are event controlled loops. They're waiting for something to happen and then they're going to stop. So we usually use an event controlled loop when we don't know exactly at our right time how long this is going to take. And so here we say while n is greater than 1, that's good. We know we've got a loop. We see a constant amount of work in line 3. I've got a constant amount of work in line 8. So they're really not important. It's only what's going on with this loop. And the loop, if I look inside the loop, lines 5 and 6, I've got a little bit of math, some assignments, 4 steps max, or 2 steps simple. N divide equals by 2, R plus plus. Both of those things are a constant amount of work. So the only thing that's going to be important about the complexity of this function is how many times is n going to be greater than 1. And since n is divided by 2 every time in line 5, I can see that I've got a division here. I don't have a plus plus minus minus. I've got a division that's controlling my loop count. And so this is going to give me something that's logarithmic. Right? Oh, one too early. In the b search function there on the far side, I've got something similar. I've got a whole bunch of stuff now. There's lines 13 through 19 that are inside the loop. But if we look closely at them, they always take the same amount of time. I've got an assignment. I've got a little bit of simple arithmetic, low plus high minus low over 2. I've got a comparison, dereference mid. Is that equal to value? Oh, I've got a dereferencing. I got a pointer action. I've got a return statement. All of the things from 13 to 19, there's quite a few steps there. Some of it conditional, but all of it is going to be the same amount of work no matter what n is. Then we're stuck with the question, what is n? Well, we stay in the loop while high is greater than or equal to low. So somewhere in there, my n is based on the distance between low and high. But if we look at how low and high adapt, we see in line 17, high gets set to mid -1. In line 19, low gets set to mid +1. So my update for this loop is either changing high or low, but both of them are somehow related to this mid. This mid calculation in line 13 is a nice overflow safe way to calculate the midpoint of two values. So we're really, when I'm finding the middle of two values, I'm taking the average of them. But I don't want to calculate my average by adding them together and dividing by 2. This may lead to overflow. So the version that I do here in line 13 says take the low spot, then subtract the difference between the high and the low and divide that by 2 and add it to the low spot. That will give you that midpoint there in a way that will not overflow. As long as low and high aren't values that have overflown, then this midpoint calculation will calculate it without overflowing. Now, if I've got really large low and high and I try to average them just by plussing them together and dividing by 2 because I think, hey, I'm gonna save some calculation time. I'm gonna get rid of one of those operations. Instead of having a plus and a minus and a divide, I can just do this with a plus and a divide. That's gonna be so much faster. It's not much faster. It's a little faster. And it also leaves you open to overflow. So be careful with that. This is a really, as I said, is an overflow safe way to calculate that midpoint. So that midpoint, though, is calculated by looking at that range and dividing that range by 2. So that divide by 2 there is going to eventually add up to something that's logarithmic, since it's what's controlling my loop there. So say both of these are logarithmic. All right, here's a nice algorithm exercise. How many multiplications if size is equal to n? That's the big question. We got a nice function here with some RME, requires an in and out. These are arrays with the same number of elements. It modifies out, and what it does is it takes any item in out and it turns it into the product of all the other items in, except for the one that's aligned with out. So out at I is equal to in at all of the other values except I, all multiplied together. So when I look at this function here, what do I see? I've got a for loop in 5, I got a for loop in 7, and everything in this function is inside for loops. So it's pretty easy to look at those two for loops. They're the kind I love. I equals 0, I less than size, plus plus I. Oh, I know that this for loop is going to run size times. That's great. What happens in line 6? That's inside a for loop. It's a constant amount of work. What happens in line 8? It's inside there. It's a comparison. It's a constant amount of work. What about line 9 now? There's a constant amount of work, but it only happens sometimes because it's inside of a conditional. Does that really matter? It doesn't if you look at it. So say I come into this for loop 100,000 times, and part of the time I is not equal to j, and part of the times it is. So it's either going to be this one step in line 8 or the 2 steps in line 9. So inside of this for loop, I can say I'm sure that this is either going to be n work or 2n work. It's linear. I don't really care. All right? So as I look at this, I can see that I've got these two loops, one's inside the other. The most important line in this, the one that gets actually executed the most, is line 8 right there. It's a constant amount of work. And how often does it get done? It gets done n squared times. So the question is, how many multiplications are there? I can say I don't exactly know, but if I is not equal to j, which most of the time it isn't, then we're going to do this line 9 here. So I would say my upper bound on that is going to be n squared. But if I wanted to be really, really close and careful about this, I see that I is equal to j once per inner loop. Great. Then I'll say that I'll do this thing inside of 9. How many times? It's going to be n squared times, but once per loop I don't do it. So it's going to be n squared minus n times I'm going to multiply, which still ends up with something that looks like it's big O n squared. Look at this version of it. This version is attempting to do the same thing. And so instead of doing each one of those products independently, it says, what if I just multiply all the values together, and then for any given output, I just divide that item away? Because remember, each of my outputs was supposed to be a combination of the product. It was supposed to be the product of all of the other items, and so we have to divide that thing off there. So this particular algorithm accomplishes the exact same thing the previous algorithm does. But when we do an analysis on it, what do we see? I've still got these two for loops, but now they're not nested. So each of them contributes some linear amount of time. We see I've got a nice plus plus I in line 3. I've got a plus plus I in line 6. Those are nice n-based for loops. So I can look at both of these for loops as taking n amount of work, and if this does the exact same thing as the other one, I would definitely choose this algorithm right here, because this is a linear algorithm, and the one on the previous slide was quadratic. But wait, what happens if I divide? Anytime you divide, you have to be very sure of what you're dividing by. When we're doing the binary search thing, we're always dividing by 2. We're great with that. We supply the 2. We know that that division can go off without a hitch no matter what. However, in line 7, we see out at I is equal to product divided by in at I. Who's in control of in? What's in there? What if there's a 0 in there? If there's a 0 in there, this algorithm fails horribly. It literally crashes, right? We've got to divide by 0. So you have to be very careful when you choose a particular algorithm, when you have got something that's input sensitive. This is an input sensitive algorithm because if I get a particular input, it might not work. How might I fix this? Well, if you're really astute and you figure out how this thing is working, you realize that if there's 1 0 in that input, then almost every item is 0 because the output are all multiplying everything except for their particular input. So the only one that has a non-zero value is where the 0 is. All the rest of the items are 0. So what you could do is in a linear amount of time, you run through, count the number of zeros. If there's no zeros, 0 zeros if you will, if there's 0 zeros, then you know that I can do this algorithm just as it stands and be done in a linear amount of time. And all I have to do is an additional linear check. Might seem like, wow, that's really slowing things down, but let's take n to where it belongs. Way up there. When n is 100,000 and you want to square n, what do we get out of that? Those of you who are fast with a calculator, turns out that that's like 10 billion work. 10 billion work. 10 billion work when I square it. So 10 billion work, do you want to spend 10 billion work, or if I do an additional for loop here that's linear, it's looking like 100,000, 100,000 plus my guard loop is another 100,000. I would take 300,000 over 10 billion every day of the week if I can afford it in memory, and I can. So it's okay to add a little bit of work to save you a lot of work. So this one would be great. If I added that extra for loop to count my zeros, it turns out if there's more than 1 0, all the answers are 0. So I could be done here in a linear amount of time in many cases, really simply. All right? So there's my algorithm exercise. It's fun when we look at our size equal to n. That's complexity analysis, counting steps. Remember, we talked about this step counting thing in a very ideal fashion. We say every one of these operations, they're all the same. They all just take 1 step. We got into seeing that some operations maybe take more steps, but it was important that our loops were what was being counted. Because what happens inside the loops, we generally think of that as being a constant amount of work. However, it's not constant when I've got nested loops, so then I have to multiply that inner loop by the outer loop. So if you're looking at something that's n times log of n, that's because I've got a logarithmic loop that's inside of a linear loop, or vice versa. I could have a linear loop inside of a logarithmic loop. I would multiply those together and get n log n. If I've got a linear loop inside of a linear loop inside of a linear loop, that's n times n times n, n cubed. So that's how we do it, by looking at our loops and understanding what's going on there. We can count the steps to see how much work a loop adds, and then we really just want to know what happens inside the innermost loop. That's where things really take time. Up next, we're going to talk a little bit about big O notation. This is something that you have seen in 203. Clap, 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 clap. Applause for the 203 folks. Big O definition here that we're going to stick with is f of n is big O of g of n if, and only if, there are these two constants, c, which has to be greater than 0, and n sub 0, which has to be greater than or equal to 0. So if I've got these two constants that says f of n is less than or equal to c times g of n, as long as n is greater than n sub 0, or greater than or equal to, then that's where I've got this big O, f of n is big O of g of n. So that sounds pretty mathy. Let's break it down. So we're going to be looking at one of our normal complexity classes for g of n. This is something like n, log n squared, n log n, and so on. So I'm looking at that, I say, well, f of n has to be less than c times g of n. And the example we've got here is, how do we know that f of n being n is that big O n squared? And hopefully you've got a feeling about that. It's something linear is always going to be less than something quadratic as n gets large. So that's what is important here. This f of n is just n. This g of n is n squared. And so the definition says as long as f of n, is less than or equal to c times g of n, n squared, then I'm good. If I've got some n sub 0. And so in the graph, there's this linear line that starts at 0 and takes off red and goes like that. And for a little bit, the quadratic is actually below that. But once we get to that n sub 0 equals 1, that's where they cross over, and the bounding function, n squared, goes above the bounded function, n, and it never goes back below it. So that's how we know that it's bounded by it. So that's what we can see it here graphically. We can look at it mathematically, and we see that it doesn't matter what c I choose with this particular pair, right? Because once I get past the place where they cross, I could be multiplying that n squared by 2 or 3 or 50 or 10,000. It would still always be larger than n, which is why I can say, yes, definitely, n is big O of n squared. Another way we can do this is what's called a sufficient condition. Sufficient means that if it shows up, we're happy to use that. But it's also not necessary, which means that if it doesn't show up, we can't say that it won't work. So it's sufficient. If we see it, we know that it's true. And that is, if I take f of n and divide it by g of n, and then send n off to infinity, and I take the limit of that value, that's going to be something, right? If that something doesn't also go off to infinity, doesn't matter what it goes to. So here I've got f of n divided by g of n. I take the limit of that as n goes to infinity equal to d. As long as d doesn't go to infinity, it could go to 4, it could go to 4,000, it could go to 1.8, I don't care. As long as it goes to something that's constant, then I can say that f of n is big O of g of n. Here's a couple of examples of that. Is log base 2 of n big O 2n? Hopefully you know that 2n is linear, and we've already said that we start out at constant, then we slow down to logarithmic, then we slow down even further to linear. So we would think that log base 2 of n is big O of 2n. But let's prove it with this sufficient condition, and we do that by dividing log of n by 2n and taking n off to infinity. How do I do that? Log of n divided by 2n. You're going to have to use L'Hopital's rule, and L'Hopital's rule says we can take the first derivative of the numerator and take the first derivative of the denominator, and then check to see if we've got something that can be limited, right? And so as I take the first derivative of log n, that's just 1 over n, and then I take the first derivative of 2n, that's just 2. I combine those, and I see that after taking the derivative of the numerator and the denominator, I've got 1 over 2n. Well, as n there shoots off to infinity, we realize that that value goes down to 0. 1 over 2 times n, as n goes to infinity, looks like 0. So that d does converge, and so I can say that log base 2 of n is definitely big O of 2n. That's great. How about this next one? This next one's got sine of n over 100. Is that big O of 100? Well, if we think about it, sine just does this. If I put some fraction or multiplication there, it's going to be higher or lower, but it's still going to be going back and forth. So at some point, it's never going to go above something. And so I can say that, yeah, definitely sine is a big O of something constant. I just have to pick a bigger constant and say, well, maybe 100 isn't enough. Remember that we had those two numbers, c times g of n. So if big O of 100 isn't big enough to go over sine of n over 100, then I can just multiply that by something with a new c. And as long as that stays above my sine, then you can say, yes, this is definitely true. So I know that it's true, but as I try to use this condition, what do I get? Well, I take sine of n over 100, and divide that by 100, and then take n as it goes off to infinity. It looks like that never converges, right? It's still doing this thing here, and so we never get a solid answer there. So what I'm saying is this condition doesn't hold, but it's not necessary that it holds. Remember, it's sufficient if I get it, but if it doesn't get it, it doesn't mean that sine of n over 100 is not big O of 100. It turns out that it is. It's just that this condition can't find it because it doesn't meet that sufficient criteria. Why do we drop our constants? I alluded to this earlier. I could say something like f of n with 3n squared plus 7n plus 42 is that big O of n squared. Well, 3n squared seems like it's always going to be bigger than n squared, doesn't it? But remember that we get to put that c in there. I can take and pick any c I want and multiply it by g of n and say, well, is that going to be bigger than 3n squared? You say, well, sure. What if I just pick like 5? 5 for c says, is 3n squared bigger than 5n squared? You're like, no. Okay, but wait, there's more. There's 3n squared plus 7n plus 42. So at really small values, 3n squared plus 7n plus 42 is larger than 5n squared. And those really small values are what n sub 0 is all about there. In the graph, there's that line at n sub 0 is somewhere about 3 3/4. Values of n that are 3 and below, my bounding function, the n squared, is going to be slower. Values of n that are 4 and above, my bounding function is going to be larger. So once we cross that n sub 0 boundary, my bounding function stays above the bounded function forever. If I want to check that same comparison, that f of n 3n squared plus 7n plus 42 and g of n squared with my sufficient condition, sure, I can put f of n squared on the top, and it looks like 3n squared plus 7n plus 42 over n squared. To take that limit as it goes to infinity, I'm going to have to take some derivatives there. So I take my first derivative, I get 3n squared plus 7n plus 42 turns into 6n plus 7. My denominator turns into 2n. I still don't have this simple enough, so I'm going to take another first derivative there, and I see that 6n plus 7 just turns into 6. 2n turns into 2. So the limit as 6 over 2 takes n off to infinity is just 3, so it is sufficient to say that f of n, which is 3n squared plus 7n plus 42, is big O of n squared. We can drop those constants because of the c and the g. So if I'm worried about the leading coefficient on my function, f of n, that 3n squared, I can pick any c I like. So I can get rid of that 3 as a consideration when I'm trying to figure out what the complexity of this is. The same thing is true for the plus 7n plus 42. Those are lower order terms that eventually, when n gets large enough, I can ignore them. So the n sub 0 allows me to dump off the lower order terms, and the c allows me to ignore the leading coefficient, which is why I can easily drop off any constants when I'm looking at 3n squared plus 7n plus 42 and just say, that's big O n squared. There's my 2 rules of thumb. I always get into the slide too early. But it's the same thing here. My lower order terms can be ignored, and my coefficient of my highest order term can be ignored. Because of c, because of n sub 0. 1 is because of n sub 0, 2 is because of c. Here's a nice page out of a math book. Some stuff you might want to know. Log identities. This is how I do stuff with logarithms. If I'm doing addition or subtraction or multiplication or division, all of these things let me work with logs. Power identities are on the next part of the slide. That's how I combine and work with exponents. So here's my exercise. I've got some questions here. 10 to the 100. Is that big O 1? Yes or no? Well, 10 to the 100, that's a constant, so a constant is always constant. So I'm going to say yes. How about the next one? 3 times n to the fourth plus 45n cubed. Is that big O of n to the fourth? Absolutely. I can pick a big C, and it's about 4 times n to the fourth. And then I pick some n sub 0 where that lower order term, 45n cubed, is not really affecting what's going on with the higher order term, the n squared. So true again. How about the next one? 3 to the n, is that big O of 2 to the n? That's not so good. Every time I add an n, I'm really multiplying both of these sides by one more value. So there's a bunch of 3's on this side and a bunch of 2's on this side, and every time I add n, I multiply this by 3 and I multiply this by 2. This side is never going to keep up. So I'm going to say false. 3 to the n is not big O of 2 to the n. How about if I turn the tables? If I say 2 to the n, is that big O of 3 to the n? Well, there it is. As I keep multiplying my function by 2, I multiply my bound by even more, by 3. And I can use my sufficient condition on that one. If I take f of n, 2 to the n, divided by 3 to the n, I end up with something that looks like 2/3 to the n. As n goes to infinity, 2/3 to the nth power goes to 0. And we end up with something that converges. So my sufficient condition can tell me this one, and that's going to get me there. How about the next one? The next one's a trick question. 45 log n plus 45n, is that big O of log n? It is not. It's a trick question because it's a poorly written equation. You're always supposed to write your equations with the highest order terms first. Here, the writer wrote this in the wrong order. And that's something that you might do on accident. This 45 log n is not the leading term. The leading term is really 45n. And that's not going to be bounded by log n, no matter what c or n sub 0 you choose. 45n would dominate here, not 45 log n. So 45n dominating makes this one false. How about log n squared? Is that big O of log n? How do we pull that off? Well, it looks at the way that logarithms work here. Look at this one right here. Log base a of x to the r is really r times log base a of x. So if I've got this log of n squared here, that's really 2 times log of n. So 2 times log of n is big O of log n. I can just pick some bigger c for that log n, and I'm good there. So that one's true. The second one, however, is false. That's not the way that logs work. Log of n times log of n is not big O of log n. And the last question on the far side is find some functions f of n and g of n such that f of n is not big O of g of n and g of n is not big O of f of n. So neither one bounds the other. That's what we're looking for. So here's what I've got in terms of my answers. I've got the first one, second one, fourth, and sixth ones are all true. That leaves me 3, 5, and 7 as all false. My 2 functions hopefully were chosen as cosine and sine, or sine and cosine. Sine and cosine are constantly going up and down. Neither one bounds the other. How about big O? We talk about big O a lot because it's a real easy way to do it, but a lot of times we're more concerned with our big theta. Because big O is the absolute most amount of work that can be done there. That's our worst case. Worst case is a pretty easy thing to pick. If you pick a really, really large function, you say, well, worst case, it's never bad. It's never worse than that, right? So if I got some really complicated equation, I say, well, what about, is that equation big O n to the 16th? Probably, but that upper bound is too far up. So we often are looking for a tight upper bound. So that asymptotic upper bound is something that's always above here. So here's the definition from the previous slide, as f of n is big O of g of n and y, and it's just a mathematical version of it. And then there's a couple of examples down below. I say, if f of n is 2n plus 1, I can say, well, that's big O of n, because 2 times n plus 1 is linear. So I can say that big O of n is linear. But I could also say it's big O of n squared, because a linear function is not going to go above a quadratic function. I could say, for that matter, it's big O of n cubed. So you see here that when we're talking about an upper bound, it's easy to say something that isn't very accurate. I know that every person in this room can't jump above 10 feet. That's too high. If I wanted to really put something in there, I'd say, well, I know nobody in this room can jump over 100 feet. And I would be correct. That's an upper bound. But it's not a very exacting upper bound. And so when we want to understand that we want to know that you understand these complexity analysis things, we're going to be wanting you to get that big O to be as tight as possible. So in the case of an n squared plus n plus 5, while n cubed would be a correct answer, it's not going to get you points on a test like an n squared would, because n squared is the tightest upper bound that we can have. On the far side over there is big omega, which is kind of the exact opposite of big O. That's the asymptotic lower bound. And that definition just reads f of n is big omega of g of n if and only if there exists an integer n sub 0 and a real number c, such that for all n greater than n sub 0, f of n is greater than c times g of n. So the function in question is always above the bounding function, right? And when that's the case, that's a lower bound here. So that's what big omega is. And then big theta, you can think of that really as being the combination of big O and big omega. So we've got a couple of different constants, C1 and C2, but if I can pick different constants C1 and C2 in such a way that f of n is always between C1 times g of n and C2 times g of n, I can say that that's an asymptotic tight bound. So in our lower bound, much like our upper bound, you could take something like n cubed and say the lower bound on that is n. Well, sure, because it's never going to go down like that. But a really good lower bound on an n cubed function would be n cubed. So big theta then doesn't have anywhere to hide. So you'll see that when I'm talking this linear equation, f of n is equal to 2n plus 1. That's a big theta of n. That can be bounded on the top and on the bottom by a linear function. And n squared plus n plus 5, that's bounded on both sides by n squared. You can keep n squared always below n squared plus 5, and you can keep an n squared always above n squared plus 5. You just pick a couple of different c's. All right, that's big O notation. Let's move on to amortized complexity. We talked about this a little bit in the previous lecture yesterday. When we talk about amortized complexity, this is one where we've got an operation that works differently. Sometimes it works like this, sometimes it works like that. So this amortized complexity is a type of worst case analysis. And it only is useful when I've got this different type of function. So we call this profile, the technical term is spiky, right? And so that means it goes like this, and then ping, it spikes. So sometimes it takes this amount of work, this amount of work, this amount of work, and then another time it'll take a lot of work. And this is the same operation now. That's why we have to do this. So if you look at the way that pushback works in a vector, when I've got capacity that is larger than my size, I can just stick something new into that vector, no problem. But when my size and my capacity are equal, I say that vector is full. And if I try to push something back in there, what do I have to do? I have to go allocate more memory, copy all of the things over from the new memory, from the old memory to the new memory, and then put it in there. So that can take a linear amount of time in n sometimes. Other times it's a constant amount of time. There's space, you put it in there. So how do I then evaluate that? Because I can't say, well, it always takes a short amount of time, because that one time when it takes a really long time, it really make you upset. So the way we do this is we perform this analysis over a sequence of operations. So we say, like, let's go from when I have a full container and push, 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 push until it's full again. So if I fill it up at n, I say I want to push one more, now I got to double n, copy those n things over, and I've got n spaces now because it goes from size n to size 2n. So if I go from n, now I've got 2n, I've got an additional new n really cheap steps because there's enough capacity for them. So the first one cost me n to do, and then I've got n minus one of them that cost me 1 to do. So I have to do it over this sequence of operations. That's the way amortized complexity works. It may work over the full lifetime of a container or algorithm, or in this case, there's sort of chapters. There's a chapter when we're at this size, and then there's a chapter when we're a double of that, and we're a chapter of the double of that. So we have to either take the entire execution or a chapter of that execution, and then we can combine all of those and say, how does that really average out? So it's really important. You're not going to be able to understand the way that complexity works on vectors and priority queues and hash tables unless you understand this amortized complexity. Here's our example for a cell phone. Imagine how cell phone bills get paid if someone else isn't paying your cell bill for you. My wife pays mine, so I don't ever have to worry about it. It's actually still my money. That's different from having your parents pay for it, and you never have to worry about it or worry about it. But all right, so you pay $100 once a month, or they pay. It's even better if they pay. All right. Once it's paid, though, we can think of all of those phone calls and texts for the rest of the month as being free. Free. So if I make 1,000 calls or texts, say each one of them costs effectively 10 cents each. So now I can say, well, what happens though on the days when I'm making phone calls and sending texts that's not a day that I paid my bill? It is essentially free. I'm paying 0. But then that one day of the month I'm paying 100, so my profile is spiky. Nothing, 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 nothing. Bill day, nothing, nothing, nothing. And so in order to figure out how that works, we have to say, well, let's look at all of those days in a chapter, or in this case, that chapter is a month, right? I start at the beginning of the month, I go to bill date, and then I get to the end of the month. So if I add all of those up, say, well, 0 cost, 0 cost, 0 cost, 0 cost, the full monthly cost, 0 cost, 0 cost, 0 cost, that's the total cost. I say, how many calls plus how many calls plus how many calls, all the calls that I add up in them. Then I can say, well, the total cost per call is going to be that total billed value divided by the total number of calls over the month. So that's an amortization. So here you could say if I'm spending $100 on my bill and I got 100 calls and 1,000 calls and texts, then each one of them actually costs 10 cents. And that's my amortized cost. And here we see that they've got a constant amortized cost here because we've done this. So, and this is of course assuming unlimited texts and calls. So a really common amortized complexity, I've talked about this already, is pushback. When I push something into a stack using an array or vector, or if I do a pushback onto a vector, then what happens is I allocate more space when I need it. And that's what it says here in line 1 there. It says, if needed, allocate a bigger array and copy the data. That's a linear step because all of the n items that exist already have to be copied. So that version of it adds n work, and then I add the new element, which is a constant amount of work. So it's sometimes just that constant amount of work, sometimes it's linear plus the constant. So I look at this as being spiky. This is an amortized constant complexity because if I'm making that growth in relation to the size of my container, then I can say this is amortized constant. So this is why we can see the math on it. So in this one, we're going to sort of analyze this. We're going from the vector being filled with n elements, and then we're going to double the size of it. And what this does is it costs me 1 plus a big theta of n's. It's always going to be n. It can't be less than n because we will be copying them all over there. So it needs to be even tighter than a big O because it can't be less than n. Copying all n of those items over there is always going to be n. So we'll double the vector size. That's one step just to get all of that memory. But to move everything from the old memory to the new memory, that's the big theta of n work. So if I start out with this thing filled with n elements, then the first thing I do is do this 1 plus theta n work that doubles it and moves it over. So now I've got how much space left? I've got n empty spaces because it was of size n, and then I doubled it. So now it's of size 2n, but I still only have n data in there. This allows me to push in n new values in a constant amount of time before it's full again. So I look at the total amount of work as being 1 plus theta n, that's the double and copy, and then I've got n times theta 1, because this is the constant amount of work to insert each one of those n items. So if I add all that up, I've got 1 plus theta n plus n times theta 1, and then I sort of divide that by how many times I get to push. I get to push n times because I doubled it, and then I had n empty spaces, and I had to fill it back up again. So this allows me to do n pushes. So if I look at my amortized cost there, it's 1 plus this theta n plus n times theta 1, which you can also think of that as just being theta n. So it looks like my upstairs is all controlled by theta of n, and then I'm dividing by n push operations. So this ends up being an amortized constant value. Let's breathe that math in for a second. This also points to why we double vectors. Instead of just saying, hey, well, it's full, let's add 100 more. And when it fills, I'll add 100 more. And if it fills again, I'll just add 100 more. That sounds great. But what happens is I take and add to the thing. So I'm going to get my memory allocation, and then I have to move the n items. So this always stays the same. This step where I'm growing memory, if I'm not doubling it, let's say I'm just doing a plus 100, my increase in size and copy is still 1 plus theta n. Then now I can only do the number of spaces that I grew it by. So this is no longer n free pushes, now it's that constant number of pushes. So it looks like I've got 1 plus theta n plus that constant, this we say was 100 free pushes now. Well, if I do that math again, and it looks like I've got 1 plus theta n plus 100 times theta 1, and that gets divided by not n any longer, because I don't get n free pushes, I get 100 free pushes. So now I'm dividing by 100, and it looks like I've got 1 plus theta n divided by 100, so I've got theta n divided by 100. That's something linear divided by a constant. It's still linear. So if I don't double, if I make that a constant growth, then I will have this behavior look like it's amortized linear. And an easy way to really sort of get a qualitative feel for that is, imagine when I've got 100 items in there and I push it and I add 100 more. That's great. Now I've got room for 200. Then I fill it and I get room for 100 more. I've got room for 300. That feels so fine. It's fine so far. 400 to 500 to 600, no problems. Nothing's going on. What happens though when I can't control n? I can never control n. When n is 1,000,000 and I fill up that extra 100 space, I got to copy 1,000,000 things over. 100 steps later, I'm copying 1,000,100 items over. 100 steps later, I'm copying 1,000,000 items over. So I'm only getting 100 free pushes for 1,000,000 work over and over and over again. This is why it starts to feel like I just feel like I'm always copying 1,000,000 items. This just is really slow. So if you grow your container by some factor that's, based on the current container size. So if I wanted to double it, then I end up with this amortized constant. If I wanted to triple it, I would have amortized constant. If I wanted to make it 50% larger, I would have amortized constant. As long as the amount that I grow it by is based on its current size, then I get something amortized constant. But if I grow it by some constant size, no matter what that constant size is, as n goes off to infinity, I end up with something that looks like amortized linear. Right, and here it is lined up with actual equations. When I do constant growth, you see the equation is 1 plus theta n plus c times theta 1, and I divide by c there. So that theta n gets divided by some constant and ends up dominating the equation here. I end up with theta n on the far side. Here when I've got linear growth though, because I've got that n in there and I can divide by n in the bottom, then it takes that out and I'm left with something that looks like constant. So this is amortized constant, this is amortized linear. This is why we change our container size by some factor based on the current container size. So that's amortized complexity. It will be on the exam. So if it's still a little shaky, do some examples, try it out, ask some questions in office hours, blow up the chat, go for it. I'm gonna wrap things up with this balance exercise. We got about 5 minutes. I'm trying to keep us on time today. And this one is pretty simple. You've probably heard of it before, but now that we're working on this complexity analysis, you can really start to design these algorithms based on their complexity. So in this particular problem, you've got n billiard balls and a balance. And a balance is a particular type of scale that compares this side to that side, and if they're heavier, if one side is heavier, it leans to that. If the sides are equal, then it keeps them nice and even. So in this particular case, we've got n billiard balls, but one of them is too heavy. So someone has sneaked a heavy ball in there. How then can I use a balance to find that heavy ball, right? The only way I can do it is with this balance. Try to describe an n squared algorithm, and this is probably the hardest one of all of them. Try to describe a linear algorithm. Or think of your algorithm that you might use here and determine which one is it. Is it a linear algorithm? Is it a quadratic algorithm? Is it a logarithmic algorithm? So we're looking for those three: quadratic, linear, and logarithmic. And then if you're slick, you can come up with a second logarithmic algorithm. Remember, we're trying to find one heavy ball out of n, and all we have is a balance. I think the first one is the most difficult because it's actually kind of ridiculous. You would never think to do it that way because you would already have the answer a bunch of times. So, what is our n squared algorithm? N squared algorithm is pretty straightforward. You weigh all possible pairs. This one versus that one, those versus the other, blah, 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 blah. If every time you weigh all of those things together and check if you find an imbalance, you do end up finding that heavy ball n minus 1 times. That's why I say this is the one that's the hardest to do, because normal human behavior would find that heavy ball and then just stop. But this algorithm, if you wrote it to compare every pair and tell you which one it was, as I said, this would find that heavy ball n minus 1 times. Weigh all possible pairs, check to see if there was an imbalance. And this is really an example of my n choose k, right? To figure out what that complexity class is. N choose k, I've got these n balls and I'm trying to look at them 2 at a time. So I end up with something that looks like n choose 2. That's how many times I'm going to be able to do this, or to be able to weigh this out. So that looks like n factorial divided by 2 factorial times n minus 2 factorial. So as I solve that, I end up with the answer is n times n minus 1 quantity over 2, which is really n squared minus n over 2, and I end up with something that's big O of n squared. So that's my check all possible pairs version. How about the linear algorithm? Now this is the one that's kind of just a fraction of that previous algorithm. I just pick one ball and compare it to all the others. Eventually I'm going to find that either the one that I picked was the heaviest one, or I'm going to run into the heaviest one while I'm holding this one, and I say, well, here it is. That's my linear algorithm. It's pretty straightforward. You can do this in n minus 1 comparisons, and you found the imbalance in the worst case. How about my logarithmic algorithm? This one's a little bit trickier. What happens here is I'm going to sort of divide these balls into sets, into 2 sets. I say, well, take half of them over here, half of them over there. The heavy side that's the one that has the heavy ball in it. So I'll throw away half of these things and then take this and cut it in half and take half of them over here and half over there. Eventually I'll get this down to one ball that is the heaviest. That's my logarithmic. Remember, I said as we're going through loops, if I'm constantly dividing my data set by 2 or multiplying my iterator by 2, then I'm going to be looking at something logarithmic. And the same is true here. I'm going to keep dividing by 2, and every group that is not the problem, I throw that away. So that's really nice because I'll end up getting n over 2 pieces of information from one comparison. I know that this half of them are not the problem. I know that about all of them. And there's this other n over 2 that might still be the problem. I do another measurement and then half of them are not the problem and half of them might be. So that's really good. That's what logarithmic behavior is. Why is this sometimes problematical? Well, not every time I divide by 2 do I get an even number. So what happens when I go and I take a number like 18 and I divide it by 2 and now I've got 9? Well, I can measure the 2 9s no problem. When I throw away one 9, now I've got a 9 left. I'm going to cut that in half. I've got 5 over here and 4 over there, and that's not going to work at all. Well, I can take that one ball and set it off to the side. Just pick one of the 5. It doesn't matter. Then I put the 2 4s on the balance, and if the one ball that I pulled out was the heavy one, the 2 4s are exactly the same weight. And I can throw away all 8 of them and go for the 1. If the one ball that I pulled out is not the problem, then the problem still remains inside one of the 4s. So I can set that 1 aside, I can set the easy 4 aside, and now I've just got 2 left. So that's why it's sometimes problematical. We have to deal with odd numbers. Which leads us to our last version here. This other logarithmic algorithm. What if I, instead of dividing it into groups of 2, I divided it into groups of 3? So let's go with that 18. I say, well, 6 and 6 and 6. If I put 6 on this side, 6 on that side, if they're completely equal, I can throw both of the 6s away and then go for that third 6. If one of those 6s is heavier, I can throw the third 6 away and throw the lighter 6 away and then just keep dividing. So I can divide it into 3 groups, and what you end up here with is another logarithmic algorithm. In this case, I was dividing by 3. This is a log base 3 algorithm. The previous one, dividing by 2, was a log base 2 algorithm. They're both logarithmic. So if I divide it into 2 groups, I get this log base 2. Is that big O of 3 of n? What if I divide by 3? Is that log base 2? Big O of log base 2? True or false? Well, we have to do our change of base on logs here. And what it tells us is that log base 3 of n is the same as log base 2 of n divided by log base 2 of 3. So I can tell that log base 3 of n is equal to log base 2 of n times some constant. In this case, it's 1 over log base 2 of 3. Log base 2 of 3 is a constant. So I can pick some other c to defeat that c. And so yes, I can say that log base 3 of n is big O of log base 2 of n, just because I can ignore constant factors, and vice versa as well. So log base 2 of n is big O of log base 3 of n. This is why we don't really concern ourselves with what the bases are. When we look at our complexity, we say if it's logarithmic, it's logarithmic. That's good enough. Any logarithmic base is just a constant multiplication away from some other logarithmic base. So they're all equivalent in terms of asymptotic analysis. The black slide means it's time for lunch. Any following questions up here? Nigel on the chat can rock that out, and then it's time to get some food. Have a good one.